second task is this. Unlike the previous problem, for this one, I think it's very easy for experienced people because they've seen similar problems before. And if you have not seen similar problems, then this one is crazy difficult. When you see this for the first time, I think it's very hard to come up with a solution. But that's part of competitive programming. You need to solve a lot of problems to see a lot of tricks and techniques. We have n rods. Each has some range, safe, stable operating range, and we want to maximize the number of rods that are within their accepted range. And there are conditions, M constraints of form this, that a pair of rods has a condition that the sum of their values needs to be exactly equal to z, or z. Now, first thing is, you can kind of intuitively maybe even guess from the names of variables, n, m, the m always connects two things, that it is beneficial to think about it as a graph. Also, you can get to this fact if you think about contradictions. If you try to create a small test where it is impossible to assign the values so they would satisfy those equalities, you will see that at least you need three values, 1, 2, 3, and you need some condition about the sum of the first two, those two, and for example, the parity doesn't match. Yeah, the unnecessary but extremely convenient way of thinking about this problem is that it's a graph. And in this graph, I have those rows, so nodes. So I have actually n rows is equal n nodes. Even the name is similar. So let's say we have that many nodes, m edges. And I have the nodes, let's say 1, 2, 3, 4, 5. Then there are edges with information. The sum here is equal to 7. The sum here is equal to 10. The sum here is equal to 3. The sum here is equal to 8, and so on. Already from that, we can detect contradictions. And there is a separate way to think about contradictions. But again, there is a well-known technique that doesn't do it separately and just immediately makes a step towards figuring out the relative values. And that is, if you know what is the sum of those two values, if you know that the sum is 7, if I told you just a single of those values, say here I told you the value here is 6, then you automatically know that the sum here is 1. And because the sum here is 10, you automatically know that the value here is 9. 9 plus 6 is equal to 15, so this is contradiction. So this was actually impossible, but I can actually continue my logic. The sum here is 8. 9 plus -1, the values could be negative, is also 8. So every value implies neighbors. And instead of thinking about a particular value here, a constant value, I can think about it as a starting variable. So this is a well-known technique that we often perform if we have sum of values. I've seen a lot of similar problems in the past where, for example, maybe even it's not a graph, but there is sequence of values, and let's say you are given the average, the arithmetic mean of every two consecutive values in an array. So if you instead saw this in the statement, so somebody told you a of 1 plus a of 2 divided by 2 apparently is equal to 7.5. A of 2 plus a of 3 divided by 2 is equal to also something, let's say 20, and so on. The way we solve and analyze and think about this kind of problems is the same. That is, you assume that a of 1 is some kind of variable x, and you see what it implies about other nodes, other variables or unknowns. Also, it's a common way to solve a system of equations, and this is what we have here. So like if I told you x plus y divided by 2 is this, from this you could express y in terms of x. Here y is equal to 15 minus x. But we don't even need to think about this problem. This was some example to help you in the future detect similar problems. Actually, forget about that. If we're here, if I say that the value of node 6 of node 2 is equal to x, then the sum is 7. So what here I have is 7 minus x. If this sum is 10, 10 minus this is equal to 10 minus 7 plus x, x plus 3. If this is 8, then what I have at 5 needs to be 8 minus x minus 3, so 5 minus x. Additionally, I have a condition x plus 3 plus x is equal to 3. So I can write on the side x plus 3 equals 3. From that, by coincidence, x is equal to 0. It doesn't really matter that much that it's 0. It's a coincidence. We just here got unique possibility of value x. Sometimes it's not unique, even if there is cycle in a graph. Let me show you an example of that. I'm guessing that if I put here 20, I put here 17. Then what I will have is, because of the 17, at 1 I need to have 17 minus x. And now if I look at this edge, 17 minus x plus 3 is not very useful, because it's always equal to 20. So there is infinite number of solutions here of this graph, even though there is a cycle, because often people will think that if there is a cycle, then there is contradiction or a single solution. Well, not always. Generally, it's a system of equations. And if somebody tells you that there are, let's say, n equations and n variables, there can be many different outcomes. What comes from that? There might be 0 solutions, so contradiction. There might be 1 solution. There might be infinite number of solutions. Okay, so you at some node imagine you put a variable x, and you can express everything else in terms of x. Actually, every node in this connected component will be either of form x plus constant or minus x plus constant. Those are the only two formats possible, because always if node is in one of those formats, if you look at its edge to some unvisited node, the math will be that if, let's say, I'm x plus 7, the edge is 20, then 20 minus x plus 7, in this case, is equal to minus x plus 13. It always gives you the second of those two formats. Of course, this is separate for every connected component. So if there is another connected component with 6 and 7 and edge between them, maybe edge of value 50, then there is here separate math. There is separate kind of variable x2, let's say. And here maybe there is 50 minus x2. Okay. So that was what I said initially is well known for experienced competitors. And now something specific to this problem is that we are given ranges, operating ranges LR, and we want the values, the unknowns, to be in such a range. So we are rewarded if x, for example, it has some good range where we want it to be. Maybe x we want to be in range from 1 to 5. And maybe in this node, we want this value to be in range from 10 to 20. And sometimes we cannot satisfy both. But because we know that every node needs to be of one of those formats, then the fact that this value 7 minus x is in this range, we can express as simple inequalities. Let's see, not sliding window. I think, or maybe I will scroll down. Let's erase this. Either you have something like this, 10 smaller equal than x plus 3 smaller equal 20. This transforms to x in range from 7 to 17. If instead you had the other type of inequality, so 10 smaller equal minus x plus 7 smaller equal 20, maybe let's use 6. Then let's transform this. That highlighted part is equivalent to, if you move x to the left side, then this is equivalent to x smaller equal than 6 minus 10 minus 4. And then this part, you need to move x to the right-hand side. X is greater or equal than negative 14. So what we have actually is that, again, it's a range for x. X is in range minus 14 up to minus 4. Turns out that each of those conditions, no matter if the variable in this node we know is equal to 7 minus x, or it's equal to x plus 3, no matter what, every blue range, the desired range from the input, gives us information about the range of x that will be good for us. So what happens is every node says, oh, if x is in range 1, 5, it's good. We get +1 to the answer. This also implies if x is in range from minus 14 to minus 4, then +1 to the answer, and so on. In a connected component, we get a lot of such information. Every connected component gives us x must be in 1 to 5, x must be in minus 4 to minus 2, x in minus 14 to minus 4, and so on. We often cannot satisfy all those requirements, but what we need to do is choose such integer x to maximize the number of satisfied conditions. Maximize the number of conditions satisfied. And this becomes a standard problem on ranges. And this one, I would expect almost everybody in Silver Division to be able to solve. This is not a difficult problem anymore. The difficult part is done. Solving this, most people, I think, will think about it visually, or at least this is what I would do. If you have range from 1 to 5, from minus 4 to minus 2, from minus 14 to minus 4, from 4 to 10, you're looking for such x that most ranges include it. You're looking for such integer position x that you maximize the number of ranges that include this x. And that's done with sweep line, so some kind of sorting. You can also do, I don't know, segment tree, maybe prefix sums, but there are many techniques that can solve this problem, and it's a well-known task in computer science. So just to discuss at least one method, the way I would do it is I would try to iterate or sweep this drawing from left to right. So I would collect every event, every value, like minus 14, minus 4, and so on. So if there are, let's say, n nodes in connected component, then I would collect all 2 times n values or endpoints. I would sort them, so I would have them from left to right. And in this order, I would iterate. At every start, we do +1. At every end, we do -1. And always the current value, +1, -1, is the current number of ranges that are active, number of ranges that include the current x. So in this order, you increase something by this +1 or -1, and you maximize the answer with the current variable. If there is a tie between some endpoint and start point, then you process the start point first, because you want to say that here at this position, this range starts, so this position counts as intersecting 2 ranges, not just one. And that's one way to solve it, but I'm rushing through this part because, again, it's the simple part of this solution. The difficult part was here. To summarize the solution to the problem, we read the input, the n nodes with some ranges that we will leave for later, the m edges. We run DFS to find connected components. In every connected component, the first node from which we start DFS, we say that there is some unknown variable x. We express all other nodes as x plus something or minus x plus something. Every node will be in one of those two formats. You can keep this as, for example, an integer and a Boolean variable, false or true, plus or minus. You mark all the nodes, so the DFS will reach all the nodes in this connected component. It will put the formulas there. Always when you see edge to already visited node, you check if there is no contradiction. So you always see if, for example, you have x plus 5 plus x plus 7 needs to be equal to 20. You always look for contradiction and you look for something that implies the value of x perfectly. For example, if you have this, so you have two neighbors with the same sign next to x, then it will give you x uniquely. In this case, twice x plus 12 is equal 20, so 2 times x is equal 8, so x equals 4. So this is unique value of x. Sometimes it will give you contradiction because of parity. For example, here we would have this. 3.5 is illegal, so you would say -1, impossible. If the two neighbors have different signs, like x and minus x, then you will either get contradiction, like here, or you will get no information, like here. This equality is always satisfied, so you don't gain anything. Then, once that's done, either you got a single x and you need to compute how many ranges in the connected component are satisfied, or you have no extra condition on x, then you start looking at the LR ranges. Every node in this connected component you need to transform into a requirement like x needs to be in range from 1 to 5. And then it's a standard task of you're given a lot of ranges, find a value that belongs to most ranges. And that's usually solvable in n log n. That being said, yeah, n log n. So because of that last part, the full thing is n log n or m log n. But everything before that was linear. Finally, the total answer will be the sum of answers from different connected components. Time for questions. I see some strategy question, I guess, unless it's about a particular this problem. How to choose which is the best solution when you have a lot of strategies? How long does it usually take? If you have a lot of different ideas or a lot of different, techniques you can think of, algorithms, and so on, then there is no golden rule about it, about the strategy of order of solving. And because of that, some problems are hard because you just cannot decide because there are many possibilities. Just certainly, I wouldn't recommend trying the first idea that you have and going very deep into it without considering other things. So maybe some reasonable piece of advice that is your problem solving with BFS, not DFS of orders or of ideas. So if you have a problem, let's see here. If you have a problem and you think, oh, maybe binary search, maybe DP, maybe this, maybe that, it's not always a great idea to say, okay, binary search is my first idea, so then I need to sort, then I need to do this, then I need to do this. After it depends on the problem, but let's say after a few minutes of this, if it doesn't seem to be an easy problem solvable this way, you need to also investigate other ideas like dynamic programming. So yeah, BFS is better if you try one idea, another idea, another idea. Then usually you choose the one that seemed more reasonable and you go a little bit deeper there, but still you have in mind those other ideas. In lower divisions, usually you don't need to go that deep into one idea before you see if it's a solution or not.